All right, our next speaker is Alexander Kalmynin on Sarkozy's conjecture on quadratic residues.
Okay, so uh, once again, I'm sorry for some background noises, and I'm very thankful to the organizers for the opportunity to give a talk on such an interesting uh, topic, at least for me. Today, I would like to discuss the proof of Sarkozy's conjecture on quadratic residues. First of all, what is the main idea? Uh, uh, Several principles in arithmetic combinatorics say that multiplicative and additive structures do not kind of mesh together. So if something is highly multiplicatively structured, we expect that it is not additively structured, and vice versa. For example, here is the Erdős-Szemerényi conjecture. So for any epsilon, we have maximum of a plus a, and a times a is at least a to the power 2 minus epsilon. This is known for epsilon greater than this fraction due to Bloom and this fraction due to Cushman. And the general case epsilon greater than 0 was recently disproved by a now famous paper by Bloom, Savin, Schildkraut, and Jelizov. Uh, so now we live somewhere in the range between this uh, and 0.0 something. Okay. Uh, the second conjecture is about cliques in polygraphs. So suppose you have a very large prime P and consider the simple field Fp. Uh, so if we have any subset A such that A minus A consists of quadratic residues, then it is conjectured that the size of of A is P to the epsilon. And the best known exponent here is the trivial one, 1/2. So the trivial exponent comes, for example, from the Cauchy-Bunyakovsky-Schwarz inequality for character sums. What I'm going to discuss here is the Sarkozy's conjecture, which states that if P is a large enough prime number, then there are no sets AB such that the minimum of A and B is greater than 1, and A plus B is equal to RP. RP here is the set of non-zero quadratic residues modulo P. We can generalize this a little bit. So let D be a divisor of P minus 1. Then we can consider the subgroup mu sub D, which is the set of these roots of unity in FP. So all the subgroups in FP star are all of this form. And in particular, we have this identity, RP is equal to mu of P minus 1 over 2. Okay, so the main results are as follows. Suppose we have a proper divisor P minus 1, and suppose that, wait, okay, so D is a proper divisor of P minus 1, and suppose that our subgroup together with 0 is a difference of some sets. Then D is either 2 or 6. And if D is not 2 or 6, and the pair DP is not 2041, then for any A with A minus A in our subgroup with 0, we have the following inequality. So not only our subgroup not a difference, it is not a difference due to element count. Okay, the second theorem is what I call the alpha equals beta theorem. So about the Levson conjecture, I will speak about it if I have time at the end. Okay, so alpha equals beta theorem is if we have a subgroup and it is a sum, non-trivially, then the sizes of summands are equal and are both equal to square root of D. So for instance, D should be a perfect square. And the third theorem is Sarkozy's conjecture. The set of quadratic residues is additively reducible for all primes P. We also get an easy consequence, which was obtained independently by Yip. So he did not use our theorems. He proved this result earlier. So his result is that no proper subgroup of FP star is a sum of three sets, A plus B plus C. This is a consequence of our theorem too. Okay, what's next? Earlier versions of theorem 2 were proved for quadratic residues. So when D is equal to P minus 1 over 2. And Shkredov proved the following inequality. So sizes of A and B are between 1/6 of square root of P and 3 times square root of P. And the best previous result is due to Chen and C. They replaced 1/6 by 1/4 and 3 by 2. Okay, and our results do not rely on any character sums, and in fact, almost no inequalities will appear until the very end of the argument. So what I mean by inequalities, I mean analytic inequalities. Some inequalities between natural numbers will be necessary, of course. Okay, so what is the proof? The proof relies on the polynomial method, and the idea is due to Hansen and Petridis. They considered the set A. So the size of our set A will always be alpha, and the size of the set B will always be beta. And we can define the Hansen-Petridis polynomial by the following formula. Ca of A multiplied by x plus A to the power D plus alpha minus 1 minus 1. And Ca of A are defined by the following conditions. So all the power sums C sub A of A multiplied by A to the M are 0 if M is less than alpha minus 1, and it is 1 if M is equal to alpha minus 1. This polynomial was used by Hansen and Petridis to prove that if A plus B lies in the subgroup together with 0, then we have the following inequality. A times B, size of A times size of B, is at most D plus the size of intersection of A and minus B. So it turns out that if A plus some element B lies in the subgroup with 0, then this polynomial has a 0 of order at least alpha minus 1 at x equals B. And if we exclude 0, then the order of 0 becomes at least alpha. I will not discuss the proof. It is easy when you know what to prove. Okay, so in particular, if A plus B is a subgroup, then A and B are cosidon. All the sums are pairwise distinct. Sums of the form A plus B, of course. Because if you have any collisions between the sums, you will not have enough elements to represent all the elements of mu D. And if we were able to replace less than or equal sign in our bound, this one, our bound for, our bound for A times B, then we will get the additive reducibility of our subgroup. Okay, so let's say that the pair of sets AB is a D-critical pair if A plus B lies in the subgroup together with 0, and A times B is equal to D plus the size of the intersection between A and minus B. One can use generating functions to prove the following formula for Ca of A. It is a product of differences between different elements of A. You take your element A and you subtract all the other elements, and then you multiply and take an inverse. In particular, you see that this Ca is actually shift invariant. This is deduced from the following generating function observation. If you consider the sum Ca of A divided by 1 minus Ax, you are going to get a formal series which starts from x to the power alpha minus 1. And it is easy to write down such a power series. It is x to the power alpha minus 1 divided by this product. Okay, so if AB is decritical and 0 does not lie in the sum, then we have the following factorization of Hansen-Petridis polynomial. So let's pause here. Is this clear? If someone have any questions about why this is true, I can. So it's okay. And it's not too noisy, right? I cannot hear you. Sorry, your mic is off.
Yeah, it's not too noisy. We can hear you clearly.
Nice. Okay, so if you now consider both these polynomials, of course, the coefficients of this polynomial are represented as polynomials of symmetric polynomials of B. And it turns out that the coefficients of this polynomial are also polynomials of symmetric polynomials, but now of A. So this identity gives us a lot of relations between symmetric polynomials of A and B. And ultimately, this set of relations will lead us to a contradiction for our D equals P minus 1 over 2. Okay, so to deal with this relation, we are going to consider differential forms on the projective line. Suppose we have some algebraically closed field K and a differential form f of x times dx. F is a rational function, and dx is, well, a formal expression. For any a in the projective line, we have the well-defined value of residue at this point, and we have the reciprocity law, which says that the sum of all residues is 0. So this is obviously very well known for say, compact Riemann surfaces, but it is also true for all say, smooth projective curves over algebraically closed fields. But now we have just a projective line, and the proof of this result is completely elementary. Okay, so example is the form dx over x, which has two poles actually, 0 and infinity. And residues are 1 and minus 1. So the residue 1 at 0 is apparent, but if you want to see the minus 1 at infinity, you need to change the variables, set x equals 1 over y, and then you get minus dy over y. And then you see that the residue is minus 1. Okay, now for the theorem 2. Alpha equals beta theorem. I don't know if one can prove Sarkozy conjecture without proving the alpha equals beta theorem, because it kind of collapses the space of relations. So if you know that alpha is equal to beta, then you know the value of alpha and beta, and then you get a lot of other stuff. So suppose that a plus b is equal to mu t, then we have this power sum condition, of course, because this is actually a sum over all subgroup of case powers, and this is, of course, 0. Now, n will be the least n such that the sum of nth powers of A is not 0, and m is the least m less than or equal to alpha, such that Pm of alpha is not 0, and n does not divide m. And so Pm is the power sum. And the formula above, this one, implies that n of A is actually equal to n of B, and m of A is equal to m of B. So in what follows, K is either n or m. We will actually prove that m does not exist, but this is for later. So we have this relation. This is obvious from our formula. And since the pair is decritical, we have the factorization. Now, we can directly compare the coefficients, but we get relations between PM and PM of A and PL of B, which become completely intractable because they involve some huge binomial coefficients, and one cannot easily prove that there are no like clear relation between them. So instead, let us do a trick. We are going to change the variables. We can do the following change of variables. So let's choose some b from b and consider the set 1 over a plus b, where a runs over the whole set of A. Then it turns out that for some constants C0 and C infinity, we have the following formula. So this is almost the Hansen-Petridis polynomial, only here we have A plus B, additional one. Okay, so, and here we have almost a factorization, only here we have also the leading term. And the proof is rather straightforward. You just take your factorization, plug 1 over x plus b, and then you notice, so this is the hard part, you need to notice something. You notice that you have the following formula. This is from the explicit formula for the coefficients. Okay, so if you look at this new identity, you can easily recover C0. This is just a binomial coefficient. This is from the coefficient at x to the power d minus 1. Then you look at x to the power d minus 2, and you get relation x. And finally, if you look at the next coefficient, you get relation y. So I'll pause for a little bit. If someone would like to ask something about these relations, I can answer. Or at least you can kind of comprehend what is happening. You have some coefficient here, and you have some 1 over a plus b, and some 1 over b minus b prime. So you have two different sums, and they are always related by this proportionality relation. And for relation y, well, it's a little bit more involved because you have both sums of squares and squares of sums. And you have also this a little bit uglier coefficient. Okay, now relation x turns out to be enough to prove theorem 2. To prove this, you need some polynomial identities for a and b. This is where the differential forms start to come into play. You can consider the generating polynomial for the set B, which is product of x minus b, and the generating polynomial for the set minus a. Then you consider the two differential forms. One takes the square of logarithmic derivative, and the other takes a product of two logarithmic derivatives, and you also add x to some power. Then if you compute the poles of, say, the first form at x equals b, you get this residue. And if you consider the pole at infinity, you get this residue. So this is the sum of symmetric polynomials, but we have chosen our k carefully so that almost everything cancels out. Okay, so now you have this lemma. If k is n or m, then we have the following two formulas. I should note that both of these formulas can be obtained by elementary means, but we are going to see much more involved formulas, which, well, they can be proved elementary, but it is much more difficult to understand what to prove than to prove it in this case. Kind of like for the Hansen-Petridis construction itself. It's much harder to understand what to prove than to prove it. Okay, so we have this formula and this formula. Then you take relation x, multiply it by b to the power k plus 1, sum over all values of b. So now you have a double sum. And this double sum evaluates. First of all, due to relation, it becomes this one. The right-hand side is already evaluated by the lemma. And the left-hand side is still a little bit unsymmetric. So we should swap A and B and get the following computation. And after everything is substituted everywhere, you are going to get two cases. Either K is even, and then we have this construction, and this is 0. So when we simplify everything, we get beta minus alpha multiplied by k plus 3 over 2. So beta is equal to alpha, actually. And if k is odd, then we get something else. This something else is this condition. So you should understand that alpha and beta are kind of small compared to p. So this alpha plus beta plus 2 cannot be divisible by p. But k minus 1 can. It can only if k is equal to 1. But we can easily eliminate this case because we can shift our sets so that the average becomes 0. So when we shift, we get k greater than 1, and then we get a contradiction. So this manipulation with exact formulas concludes the proof of theorem 2. Theorem 3, which is Charcot's conjecture, is much harder. So you need to utilize relation y. At first, I was not able to do this at all, but then I tried to kind of keep track of everything that I got. So all the relations that follow from our definitions, and then you get some strange constants. Constants gamma naught, gamma 1, and so on, which are elements of the finite field. Gamma naught is this product, gamma 1 is this product, and then you get more involved stuff. More involved stuff comes from the cubic differential forms. When you take a product of three things. So when you take a product of three different things, you write down the reciprocity law, and then you get the following formulas. For example, if k is n or m, then this big sum, it simplifies to gamma 2 times pk of b. Gamma 2 is this polynomial expression in alpha and k. So gamma 3 is this one. Gamma 4 is already a product involving gamma 0 and gamma 3. And you also get gamma 5, which is this. I'm sure it is already unlistenable at the moment, but I'll get straight to the point. So now you keep track of all the stuff you get, and essentially you have four different objects and 5 different relations. So you have 5 constants, sorry, probably six relations and four objects. And so you get a relation between gamma I. Relation takes this form. So this is one rational function of gamma I is equal to the other rational function of gamma I. And then you remember that actually alpha squared is equal to p minus 1 over 2. So you can compute everything as an element of the following ring. And then when you simplify, you arrive at the following formula. This formula is a quadratic equation for k in terms of alpha. But k can take 2 different values, n and m. If m exists, then we have a contradiction due to, say, Vieta theorem. Well, you get this formula, and this formula is a contradiction because n and m are both at most alpha. So the left-hand side is at most 38 alpha, and the right-hand side is at least 40 alpha. And this is a contradiction. So this implies that m does not exist. And so n divides alpha. This is because if all the symmetric polynomials are 0 until n, then you can assume that either A or B does not contain 0, and so n should divide alpha because the highest symmetric polynomial is non-zero. And so you get the following condition. You multiply this by 6 alpha minus 1. This is a simple calculation which follows from kind of an arithmetic of Gaussian integers, I think, or something like this. So you basically multiply by a conjugate. And from this, you get the following expression. And this is actually already a victory because n and alpha are kind of order square root of p. So this expression is kind of order p. And so you have a finite number of possibilities for the value of this. And indeed, you get this formula and this coefficient 2m. M is between 0 and 5. And so if we look at that, we understand that n divides 2m plus 18. Well, it is not really clear from this formula, but you can manipulate this a little bit and see that n is a divisor of 2m plus 18. Okay, so this would mean that there are only finitely many possible values of n, and so finitely many possible values of alpha and of p, which concludes the proof. So the actual proof for all prime numbers, it considers different possibilities, and one of the possible exceptions is one of my favorite prime numbers, 163. But fortunately, 163, or maybe unfortunately, 163 is not a counterexample for the Charcot's conjecture. Okay, so now I have some open problems which follow from a more symmetric proof of theorem one. I will not stop on that too much. Also, the techniques from this result were already used by Kim, Yip, and Yu to prove that the shifted multiplicative subgroup is never a ratio set. And some other similar results. So I think I should stop now and ask for your questions.
Thank you, Alexander. We saw a talk from you about an hour ago on that last result. So
Okay, so if there are no questions, then I can take like 3 minutes to tell a story about the Leveson conjecture. So the first conjecture in this list that I was able to solve was the Leveson conjecture. It was about the set of quadratic residues. They conjectured that the set of quadratic residues is not a difference unless P is 5 or 13. Actually, they conjectured something much stronger, much weaker, that this is not a difference with conditions that all the non-zero elements are represented as difference in exactly one way. When Lev told me about this question and said that they tried to solve it but could not, I said, oh my God, this should be completely trivial. I will take like a pen and paper and get back to you in 30 minutes. Then 8 years elapsed, and I was finally able to answer for my arrogant words.
Thank you very much. Our next talk is in 2 minutes. So.
Thank you.